Problem 1 states the compound with the proton NMR spectrum shown has the molecular formula C4H7O2Cl, and it also indicates a strong IR absorption peak at 1740 inverse centimeters. Propose a structure consistent with this information. All right, so we have an IR absorption peak 1740. That should be a dead giveaway that we have a carbon-oxygen double bond in our molecule. Since we have a molecular formula, we should go ahead and calculate degrees of unsaturation. That will give us a better idea of what kind of formulas we might propose. So this would be 4 carbons, and then we're going to subtract from that half the number of hydrogens, which is 7, and add the number of halogens, which is 1. And then we're going to add 1 to all of that, so this should give us 4 minus 4 plus 1 equals 1 degree of unsaturation. So that means we have 1 ring or 1 double bond, and we've already accounted for the 1 double bond. So somehow we have a carbon-oxygen double bond in our molecule. All right, so that's a great place to start. And so now what we have is a proton NMR spectrum. So let's look at the features here. We see a singlet here. So a 1 peak that integrates to 2. So this is a CH2. We can tell that by looking at it. And what we know about this, because it's a singlet, we know it has no neighbors. No neighboring hydrogens, that is. Okay, so singlet, no neighboring hydrogens. And also notice the chemical shift, 4. So that means it must be near electronegative atoms. Okay, so just looking at that, we know we have a chlorine, so it would be reasonable then to propose that we have a chlorine attached to one side of that carbon. And then we have some group, let's just call it Y for now, that is not, atom Y is not attached to any hydrogens. Okay, so we've got this fragment of the molecule. Well, what else do we have? We have a quartet right here that integrates to 2. So first of all, we know this is a CH2, a different CH2, and we know that it integrates because it integrates to 2, and because it's a quartet, so 4 peaks in that signal, we know that it must be next to a CH3. Well, interestingly enough, we have what appears to be a CH3 as we look over here at this peak at 1.4 ppm. So this must be a CH3 because we see this integration of 3, and it must be next to a CH2 because it is bound to, or because we see the peak split into 3 peaks. Because it's always the number of neighbors plus 1. That's how many peaks we see it being split into. So we CH2, CH3, so that is an ethyl group. And anytime you see this quartet triplet pattern, it indicates that there's an ethyl group around. Now if we go back over here to the CH2 that's bound to the CH3, notice its chemical shift. It's all the way up here, about 4.3 or something. So it must be bound to an electronegative atom. And if we look at the formula, we have a quite electronegative atom in oxygen, so it's likely that this CH2 is bound to an oxygen. And so if we look at what we figured out from the spectrum, we know we have this fragment based on the IR data and degrees of unsaturation. We know we have this fragment from those other signals, and we also know we have a CH2Cl fragment. And so based on the data, we could just combine all of these things together to get at the structure. So this would be Cl, CH2, C double bond O, O, CH2, CH3. So this is an ester functional group, C double bond O, O, 2 and more carbons. It is possible originally that this chlorine, that this could have been an oxygen on that side, in which case this ethyl group carbon right here would have had to be attached to a chlorine. And actually that isn't quite consistent with the data, because we know that oxygen causes things to have chemical shifts near or above 4. And the reason that this CH2 right here is above 4, or just barely above 4, is because it has both this carbon-oxygen double bond on the right and then the carbon-chlorine bond on the left. So both those add up to give it a very large chemical shift. So that's the structure of this compound. All right, problem 2. Propose a structure given the following spectral information. And we're given a molecular weight, 122. Okay, so we could arrive at some possible formulas, but it may be easier to just look at some of the data we have first. So looking at the proton NMR spectrum right here, there are some things that should jump out. One is that we have 4 H's in this aromatic region, around 7 to 8. So we have 4 total hydrogens. This points to a disubstituted benzene ring. And furthermore, it points to a benzene ring. The disubstitution is not para, because if you look at these signals blown up, they're not nice doublets like we typically expect for that situation. So it must be a case where we have a benzene ring that is 1,3 substituted, or ortho, or I'm sorry, that's meta. Or 1,2, which is ortho. Right, and that would look like this, where we have X and Y on adjacent carbons. Okay, and so thinking about that, if we look at the splitting patterns, this set of peaks right here appears to be a triplet. This set appears to be a doublet. Here looks like a triplet. These 2 peaks look like a doublet. And it's hard to see because they're all stacked up on there. And since we see that pattern, 1,3 substitution would not give that, because this hydrogen, because it has no hydrogen neighbors, would appear as a singlet, because there's no hydrogens adjacent to split it to a great extent. And we don't see a singlet here. And so this pattern is more consistent with this 1,2 ortho substitution pattern. All right, so with that in mind, now we can think about what are X and Y. Well, we see that there are 2 other hydrogens in the structure. We see that we have a singlet, 1H singlet at 10 ppm, and immediately this tells us that that is an aldehyde. Anytime you see a singlet at around 10 ppm, think aldehyde. And then we have an exchanging hydrogen at about 11 ppm. So anytime we see hydrogen exchanges, that means that that hydrogen is attached to something like an oxygen or a nitrogen. In this case, usually around 11 or 12, this means we have an OH, and it either means it's a carboxylic acid, or sometimes phenols will show up around there. So we either have a phenol, so this on a benzene ring, or we have a carboxylic acid. All right, so we'll just keep that in mind. That's what we can tell right now. Let's look at the rest of the information we have. So if you look at the IR spectrum to the right here, we see that we've got something around 1665. This confirms our observation that we have an aldehyde at least. We notice a big OH peak around 3300. This is really suggestive that we have an alcohol. And so look from the IR, it's pretty consistent. Also notice these two peaks here at 2756, 2849. Those are a clue. We'll come back to that before we finish here. All right, the last thing to look at is the carbon-13 NMR spectrum. All right, and let's count the total numbers of peaks that we have. Looks like we have 1, 2, 3, 4, 5, 6, 7. So we have 7 peaks. Well, let's think about our potential structure here. So we know that we have an aldehyde. And so if we think about our aldehyde, how many carbons does this have? 1, 2, 3, 4, 5, 6, 7. Well, we have 7 carbons already, so it must not be the carboxylic acid. The other group attached to this must be just a simple OH. Because now this structure has 7 carbons. So it's looking good. And just to come back to these IR peaks, whenever you see this combination of peaks at 2700, 2800, in that region, 2 of them, this actually is a secondary stretching mode for aldehydes. And they always have 2 stretching modes. So sometimes if you have an aldehyde, you'll see those peaks in there. Okay, so this structure appears to be pretty consistent, but just to double check, let's make sure that this structure that we've come up with matches the molecular weight that was given. So what we need to do is think about the molecular formula. So this has 7 carbons, so this would be C7, and we've got a hydrogen there, there, and there, so that would be 6 hydrogens, and then we have 2 oxygens. So O2. So if we add those all up, 7 times 12, it's 84. 6 times 1 is 6, and 2 times 8 for oxygen is 16. So when we add those all up, we get, what do we get? We get 10. $106. Let's see, what did I do wrong here? Because that does not make sense. All right, and this is where the part where I realize I'm an idiot. So well, we all know that oxygen is 16, so this would actually be 32. And so those all do add up to 122. So very good. All right, so that checks out. So it looks like we should have come up with the right structure. We were able to figure out the relative arrangement is at 1, 1, 2, 1, 3, 1, 4, based on this aromatic splitting pattern. We see that identified an aldehyde and phenol based on the IR and proton NMR spectrum, and by carbon 13 we were able to see that we expected 7 different types of hydrogens, which is what we saw, and the structure we came up with matches the molecular weight we found. All right, problem 3 is label the different types of hydrogen atoms and then tabulate the predicted NMR signals, that would be proton NMR signals, and sketch the spectrum. All right, so let's go ahead and label all these different types of hydrogens. We're going to have the implied hydrogens on these positions. And so as we go across, we'll start on the left-hand side here. So these would be type A. The 2 hydrogens on either side are going to be type B, type C, D, and E. And of course, this is all arbitrary. This is just, I decided to start at the left and label them. So that's what we're coming up with. Now, because we have this symmetry down the middle, that's why HBs are the same and HCs are the same. But because the right and left-hand sides of the molecule are different, HB and HC are different. Okay, so if we go and look at the expected signals, so we're going to look at type of hydrogen, and we're going to look at the chemical shift in ppm. We're going to think about the integration and the splitting. Okay, so if we look at HA, HA is a methyl it's an aryl methyl. It's attached to a benzene ring. If you look at your table, aryl methyls typically show up at about around 2.3 ppm. And because there are 3 of those, we'd expect an integration of 3. And the splitting, because there are no neighbors, we expect a singlet. HB is on a benzene ring. And typically if something's on a benzene ring, we're expecting something around 7.2. And that's close enough for government work for right now, as we're trying to sketch this out. We could go through the tables and estimate it a little bit better, but we'll leave it there for now. And there are 2 HBs, so we're going to call this going to be 2 H's. And each HB has only HC as a neighbor, so it has 1 neighbor. Because it has 1 neighbor, we would expect its signal to be split into a doublet. So remember, this is always number of neighbors plus 1. HA, HB, and then HC is going to be similar to HB. 2 H's, doublet. HC has HB as a neighbor. Now, the delta, this chemical shift, is going to actually be a little bit higher, because if we remember this system here where we went through some examples like this, that carbonyl is withdrawing electron density, which is going to make where HC is a little bit electron poor. So if we do resonance structures, we would see that HC and where the C next to the CH3, those are all a little bit electron poor. So if we went through the table, we'd probably find that this chemical shift is going to be a little bit higher. Let's say 7.6, although it might be a little different, because those HCs are a little bit electron poor. All right, and then we have HD and HE. HE is next to an oxygen that's part of an ester. So it's going to be, we just saw an example like this, it's probably going to be about 4.2, somewhere around there. But 4 is close enough. And there are 2 of those types of hydrogens. And because all the HD has 3 neighbors, the methyl group, it's going to be a quartet. HE, because it's not as close to that oxygen, is probably going to be somewhere around 1.5, give or take a couple ppm units, or tenths of a ppm unit. And that's going to integrate to 3, and it will be a triplet. All right, so now we've made it this table. It's really easy to go and plot this on our sample spectrum. So we know that we only need to go up to about 8 ppm. So we're going to go from 8, put 0 over here. Okay, and so we've got highest shift is 7.6, and that's going to be a doublet. And then we're going to have another doublet nearby. So this is going to be HC, this is HB. All right, and then the next signal going down is HD, showing up around 4.2, and that's a quartet. That's above 4. Okay. And then we have HA is at 2.3, and that's a singlet, 3 H's. And finally, that's 3 H's, so it's probably going to be a little bit taller than that. HE is going to be around 1.5, and it will be a triplet. That is 3 H's. Oh, I guess the other one was 2 H's. It's a triplet. Okay, so when we go and that's our chemical shifts, and we know that this is going to integrate to 2. And over here, this is HD. So HD is going to have an integration also of 2 hydrogens. So when we looked at the integral curves, it's going to be the same height. And then next we have HA, and the last one is HE. And both of those are 3 hydrogens. They're a little bit bigger, and so that when we look at the integral curve, it's going to be about a third taller. Okay, so there's our beautifully drawn 1H NMR spectrum. So the last part of this question was, how many signals are we going to see? Well, all we're going to do is count the unique number of hydrogens, and we're going to circle those in green. So we have CH3, we have a carbon there, carbon here, carbon here, carbon there. Notice that the carbons across from the ones attached to HB and HC are the same because of this line of symmetry. And so when we look at this, we expect 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon-13 NMR signals. All right, last one. We have a bunch of data, spectroscopic data, and we're asked to find the structure and assign the peaks to show that, well, we drew the right structure. Okay, so we have a few things. Here we have a mass spectrum. We have proton NMR, we have carbon-13 NMR, and we have, down here on the lower right, an IR spectrum. So we have lots of information here. And let's first look at the mass spec. So here, this value at 96 with M+, that tells us it's our molecular ion peak. This means that our molecular weight is around 96. Okay, and then there was some fragment in this that is 68. So there must be something pretty stable that's 68. That may or may not be important, but we can always check our work at the end and see if our formula corresponds to something that is 96. Okay, if we look at our IR spectrum, look here at 1685. This tells us that we have a carbon-oxygen double bond in the molecule. And then if we draw a line here at 3000, here we have the expected sp3H bonds, but there is a peak above 3000. So this means we have an sp2 carbon bound to an H. So this tells us we have an alkene or a benzene ring. Okay, so we're getting more and more information. All right, let's look up at the proton NMR. When we look at that, we see a peak here around 6 ppm and just above 7. And notice that these only integrate to 1 hydrogen. So this tells us that the structure really cannot be a benzene ring. If it was, it'd be a benzene ring with 4 substituents on it. If we had such a thing, it would surely have a larger molecular weight. So what this strongly suggests is that what we have is an alkene. So somehow we have a carbon-carbon double bond, and these hydrogens are coming off it. They may or may not be coming off the same carbon. But given the fact that we have a nice doublet here, and then this, the one that has a larger chemical shift is much, has a doublet, what appears to be a doublet of triplets. This suggests that those hydrogens are sort of in probably on different carbons, because one of those must be closer to a CH2 group. So let's say that this is a nice doublet and it is isolated from a bunch of other signals. All it sees is hydrogen over here. Because this is the doublet of triplets, there must be a CH2 bound to that same carbon. Perhaps there are other options, but that seems to make sense right now. Okay, we know we have a carbon-oxygen double bond. And what else do we have? Well, we see we have a CH2, another CH2, and another CH2. But if we look at these two signals, right, that's a CH2, and this is probably just two CH2s overlapping with each other. And if we look at the carbon-13 NMR, what do we see? Well, it appears we have a CH. Those are our two alkene, because if we look at the chemical shift, that's where we typically see alkenes showing up. And then we see 3 CH2s, which we've accounted for on the proton NMR. So we look at those two, or these 3 peaks there. And then it says we have a signal here, which is a carbon. And apparently we just can't see that peak. Well, whenever you see carbon peaks around 200, this is also indicating that we have carbon-oxygen double bond. Okay, so this all works out nicely. The problem is we don't know what the other groups in this molecule are. So let's figure out what we know so far. We know we have CH2, we have another CH2. It's likely that two of those are next to each other. We know that we have carbon-oxygen double bond. We know that we have carbon-carbon double bond with a hydrogen, another hydrogen, and we know that we have a CH2. So let's add up all of those numbers and see what atoms we're missing. So we know we have 1, 2, 3, 4, 5, 6. We have 6 carbons. We know we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And right now we're seeing 1 oxygen. All right, so when we put this all together, we have 6 times 12, which is 72, 8, and 1 oxygen is 16. So it looks to me like that is 96. Oh, okay, so we've actually accounted for all of the atoms somehow. Yet we have kind of a CH2 that's by itself, another CH2 that's by itself. So the only way that this will work out is if those are connected. So what we must have here is actually a ring. So let's see if we can put that together. We know that this hydrogen here is isolated other than the other alkene hydrogen. So our double bond, carbon-oxygen double bond, must be right there. So let's see how many carbons we have. 6 carbons. So this must be a 6-membered ring. And we have a carbon-oxygen double bond right there. All right, so let's go ahead and see if this all works out. So here's our structure. And so we will call this HA, HB, those are HC, those are HD, and these are all HEs. Okay, and so HA we know is kind of isolated by itself. This must be HA as we've labeled it. The peak above 7 must be HB. And that makes sense because if we think about those resonance structures again, we have partial positive charge on this carbon, but we also, if we drew a resonance structure, we'd have a partial positive charge on that carbon. So it makes sense that that HB would have a higher chemical shift because it's more electron deficient. So the shielding, it's going to be deshielded. All right, and then these 3 groups must be H, C, D, and E. And let's not worry about assigning those for now. All right, so there are all those signals. And so this matches up our mass spec data. Wonder what that fragment at 68 is, though. So 96 minus 68 in the mass spec. What does that correspond to? This would be 28 So we're somehow losing something that is 28. So 28 probably corresponds to the loss of a carbon-oxygen double bond, or some such thing. But overall, the data all corresponds to the